Hello again everyone, welcome back to ptet.chemistry channel. In this video, I'll talk about free radical substitution reaction. So before I actually get started, there are a couple of things you need to know about what a free radical is and what is a substitution reaction. So we talk about substitution reaction, meaning that we replace one atom, I would say, well, depends. We're replacing one thing with another. But when I say one, is it really one or it could be multiple? Okay, as long as you are replacing one or multiple things with something else, the idea is replacing. Okay, and they could very easily ask you to define what is meant by substitution reaction. And you first come across this term in your O level, in your GCSE, or in your whatever IGCSE, where you would be expected to know that since alkane cannot undergo addition reaction because it's only got saturated bonds, carbon-carbon single bond, it has to undergo substitution reaction, okay? So free radical refer to species with unpaired electron, okay? And to think about that, it's not something you would normally associate organic chemistry with, but there is a class of reactions where we talk about homolytic fission. Okay, so I'm going through some terminology first because it's important to know the basics behind the organic chemistry. That is what you started out with, yeah? So I've basically skipped all that, assuming you already know your basic, which you should do, I guess, by this time, if you're preparing for an exam. But if you haven't, then I suggest you read through your books and go through your lessons again and see what you actually understand, yeah? Fission refers to splitting. It's the opposite of fusion. Fusion means you come together. Fission is splitting or breaking, okay? Well, not really. It's basically breaking apart, okay? Is it splitting, breaking apart? Well, I know lytic is referred to breaking or splitting. So they are kind of together, aren't they? Okay, when you see lytic fission, they're kind of breaking or splitting. They have the same idea. Homo refer to same. Okay, so what is this homolytic fission then? Well, free radicals in this free radical substitution reaction, we usually start off with something like a chlorine molecule, which is like that. Okay, so we show that display bond there because it's got 2 electrons in between the chlorine atoms. This is a Cl2 molecule, 2 electrons in this covalent bond, one covalent bond, 1 electron from chlorine, another one from chlorine. Okay, in reality, there's actually 6 more electrons on each chlorine in the outermost shell because it's group 17 elements, so it's got 7 outer shell electrons. We only use 1 for bonding. Okay, so what is this homolytic fission? I want to skip using that because it's got quite a lot of electrons, so it's quite confusing. I was just showing it to show that when you draw a dot and cross, you gotta represent it as a cross dot or whatever. Okay, but chlorine still has got other outer shell electrons, yeah? Homolytic fission represents a type of breaking or splitting of covalent bond in such a way that the electrons in the covalent bond are split equally. Meaning to say, there are 2 electrons here. When I split it, they are split equally, meaning 1 electron will go here, 1 electron will go there. To show that, we use arrow. To show mechanism, we use arrow. But we are talking about homolytic fission, so we are talking about half-headed arrow. This is a half-headed arrow because it represents a flow of 1 electron. A full-headed arrow, like this, is 2 electrons. Half-headed arrow is 1 electron. Okay? So what are we talking about? We are talking about splitting, right? We are splitting the covalent bond. We are doing it by homolytic fission, so we are going to split it equally such that 1 electron go there and 1 electron go there. In doing so, what we have got is we are going to get chlorine radical, where this chlorine now has unpaired electron because these are paired, these are paired, these are paired. So essentially I still have the paired electron, but now I have an unpaired electron. This species is now a radical, and that equation is not balanced because I will get 2 of them. All right. I guess it's better if I draw it out, write it out as an equation, because we're going to start by doing that. Chlorine will undergo homolytic fission in the presence of UV light, that is your ultraviolet light, and it will give you 2 chlorine radical. That is your initiation step. So if you're asked to define what is initiation, initiation is basically the first step in the free radical substitution reaction, where you have your halogen, such as Cl2, also could be Br2. If you are given other contexts, you could also think that Br2 could undergo similar thing like that, and it will give you 2 Br dot. That is also an example of an initiation reaction. Initiation reaction from no radical to forming radical. That is how you identify initiation, yeah? From no radical on the left hand side, and you are forming radical. Okay? Now, I have shown 2 different things here. Are they the same? Could I draw the arrow on top as well? I mean, yeah, you can. I have drawn it here simply because I want to show you that you're not confused. But is this half-headed? Yes. Is this half-headed? Yes. So 1 electron go to each. Is this half-headed? Yes. Is this half-headed? Yes. Am I breaking the covalent bond? Yes. Where is it coming from? It's coming from the covalent bond. 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 Okay? So that's the most important thing. You could draw them on top together like that, but as long as you use half-headed arrow to show the flow of 1 electrons, yeah? Okay, it's important to show that as a cross, single cross or single dot to represent them as radical. Okay, moving on. So the second step after you get this radical, so these are very reactive species. They are not going to lie around like that, yeah? Okay, I guess we can do a very simple examples. What is it? So in books, I guess in textbook, you always see CH4 as your example, right? Let me choose something complicated. Okay, let me not choose something complicated. Something more exciting, but not too complicated. Something which is you don't usually see in books. I don't know. I mean, okay, maybe I should go simple. CH3, CH2, CH2, CH3. Let's say go 4 carbon. So usually in books you get 1 carbon or 2 carbon example, right? I'm showing you with 4 carbon. Could you write structural formula? Yes. Or you could use molecular formula. It's make no difference, yeah? So you have done this in O-level as well. So there's C4H10. So if you have an overall equation involving that reacting with chlorine, let's say you go to C4H9Cl. This is your overall equation from your reactant to your product. Now, in A level or in AS level, they could ask you in A2 as well, you got to write a series of free radical substitution mechanism to show the formation of this. All right, so how are you going to do that? Started from this, and obviously you need UV light and the Cl2 in order to do the substitution, because this is alkane and you are substituting the CH bond of the alkane, and we know it's alkane because of the general formula, which you can break it down into the structural formula. There's an alkane with no carbon-carbon double bond at all. All right, so initiation is going from no radical to radical. How about propagation then? Propagation means you are reacting a radical species. React a radical with non-radical. So I already have my first radical. I am going to react it with my substance which is not a radical. So it's C4H10. When that happens, a radical plus something with no radical, okay, what will happen is it will take out a H, it will take out the H from there, okay, and it will form a HCl. So this is going to look really weird. I'm going to draw it like that. I know you're used to seeing HCl. Is this the same? Of course it's the same. The molecule can rotate around, yeah, okay, so these molecules are the same. Whether I write HCl or ClH, this is just less common, but I'm trying to show you that the Cl take away a H. When you take away a H, now you become a molecule where the electrons are paired. What does that mean? That means something else must become the radical. I take out a H, therefore I have C4H9, I have 1 lesser hydrogen. Now I have a radical. This is a propagation because it propagates. Okay, it just keep on going. Propagate means it just keep on going, all right? You have a radical reacting with no radical. So basically, propagation involves a radical forming another radical. When you see a radical forming another radical, that is called propagation, all right? But seriously, if you don't like me drawing this, you are more than welcome to just simply write HCl, which I can do right now. Okay, so that looks better, okay? Because that's what you're used to. All right, but what will happen to this? You see, you don't need a lot of UV light. You only need the UV light to kickstart the reaction. Because what happened afterward is the Cl2 is the reactant, right? So the reactant will keep on reacting. But the reactant doesn't keep on going through this to form this, because how else can I get the radical? I can keep on getting the radical not from the initiation, because once they start propagation, the Cl2 can react with another radical, which is that. Now this is a radical, this is reactive. This is not reactive, but I don't need more UV light. I can use this reactive radical to take away a chlorine. When I take away a chlorine, I will get C4H9Cl. Recombination, yeah? So just now I lost a H to the Cl there and become a radical. Now I just take away a Cl dot. I take away a Cl dot. Now I become a molecule again with not a radical. But it's a propagation, I will form another radical. I take away one radical from there. Remember, when you break this thing, you take away one radical, you form another one radical. This is still propagation because you go from a radical species, which is this, to forming another radical species. All right? So propagation is quite hard to control. In fact, free radical substitution is what they call chain reaction. If you have heard of chain reaction, you might have heard of nuclear power plant, yeah? In radioactivity, nuclear reaction is what we call chain reaction because it's difficult to control. You cannot get exactly what you want, all right? So there's no particular selectivity, like I want to stop here. Not really. This is reactive. Guess what? This is reactive. It can react further with this and lead you more and more substitution. Okay, I'll show you one more example, which you can practice until you substitute all of them, I guess, all right? So the next example is, this is my reactive species. I can react with either this, but they'll give me the same thing. So I'll just react with the next thing and give me more substitution. So what would that give me? They will give me HCl again, but then they will give me another radical, C4H8Cl. I already have one Cl here. I don't want to take the Cl because if I take out the Cl, I will just form Cl2. Okay, I take out the H. The HCl bond is shorter and it's a stronger bond. It's better than reforming ClCl, okay? So you can talk about bond energy here. They love to combine this type of questions with bond energy calculation. If you revise your topic on energy changes, you will understand why that is. You think about what bonds are being broken. You think about what bonds are being formed. These are all in gaseous phase reaction. Therefore, you can use bond energy to work out enthalpy change. All right. So the next bit really is more of the chlorine molecule, which is not reactive. It can react with the radical to give you another substituted product. Now you have gone from 1 chlorine to 2 chlorine, but 1 lesser hydrogen because you replace the CH, you replace the hydrogen with chlorine. And so on and so on and so on and so on. Can I choose to stop here or here? Not really. On paper, it looks good. In reality, not really. Do you need all that step? Most likely, you just need these 2 steps because it shows the formation of the product that you want in the propagation, which is not 1 step. It proceeds via these 2 steps. Okay, stepwise, yeah? If they ask for more steps, obviously you can draw more and more and more and more. Okay? But it's an exam, so they typically do not ask you to do more. But when you are trying this in classes, you should try and practice with more and more substitution so that you get the hang of it, yeah, when practicing mechanism. Termination is the opposite of initiation. Initiation requires energy. This is endothermic, you are breaking. Termination is exothermic, you are forming, you are reforming. So it's what we call reforming radicals. So the radical and radical will come together. If you want to form this product in a termination step, well, what do you have? You have C4H9 radical, C4H9 radical, you just come together with a chlorine radical, and then you can get C4H9Cl. Hey, your product. But this is the product formed in the termination step because radical plus radical form no radical, right? Termination involve radical recombine. Two radicals recombine to give you no radical. If you want to form this product in a propagation, propagation means something with a radical on the reactant side forming another radical. Okay, so it's still going on. What else can form in termination? Well, can I control what I want? Not really, okay? This can happen as well. I mean, you could get C8H18 as a result of recombining these two together. It's just a possibility, yeah, okay? What else could happen? Well, your chlorine dot and your chlorine dot can recombine and give you more Cl2. And where does this go? Well, this can go here, here, wherever. I mean, it's a chain reaction. I cannot control it. You cannot control it. You might think you can control it, but you can't, okay? That's why like free radical reaction is not the best reaction in the world in terms of selectivity. Yeah? Of course, there are certain conditions that chemists and industrial chemists can do to get certain things in greater proportion, but in reality, it's very difficult to control. But this is the free radical mechanism case studies. I have just shown you with one particular example. I would advise you to go away and practice with other examples. Try a branch alkane or try something else. But essentially the idea is you substitute the hydrogen of a CH, okay, of an alkane with a halogen such as chlorine. You can try with bromine, okay? So chlorine, bromine, similar, yeah? Okay, so this is free radical mechanism. It involves homolytic fission in the first step, which is your initiation. It involves propagation, where you have radical forming other radicals. And then it gets terminated in a series of possibilities, okay? Possibility because there are other possibilities as well, okay? I'm not saying that these are all. There are other possibilities. Depends on, are you being asked on suggest a termination step to produce the product or suggest what could happen in the termination step? That means it's open. Or it could be specific. They want you to form certain thing in a termination step. Essentially is radical must recombine with another radical to give you a product with no radical. Okay, so that's it on free radical mechanism, free radical substitution mechanism. So if you like this video, stay subscribed and I'll see you in the next video where I talk about other chemistry concepts. Okay, thank you for watching.